Welcome everyone. First lecture on Nick Werner, and we're very happy he will teach us about black holes and microstate geometries. First lecture today, and then will be the next three chapters. Okay, please.
Thank you. Especially want to thank the people who came by the RERC. That was a very worthy undertaking. So a couple of warnings before I start. I tend to talk very fast. To solve that problem, I have printed out copies of the lecture notes. They're also available online. This is the only time I'll print them out. You should get them online, and I'll put them there usually beforehand. So far I've written up the first two lectures. I don't guarantee to write up the third, well, maybe the third, but the fourth I might run out of gas. But okay. So the other way, since I talk fast, is to ask questions, jump in, and so forth. And the first lecture is also especially difficult because there's an impedance mismatch. I have no idea really what your background is. I've got rough expectations, but if you have questions, then we can develop some things in different directions. Okay, so first of all, I should talk about what we are talking about and what we're not talking about. So this really is a course about solitons and supergravity. And I'm going to make a few introductory remarks about solitons and how important they are, and how they're sort of somewhat ill-defined. Roughly speaking, a soliton is a sort of classical lump, sometimes also in quantum theory as well, lump, as Sidney Coleman would call it. It's a localized, non-dispersive, finite energy solution to usually nonlinear equations or nonlinear system. And it's important it's non-dispersive, it maintains its integrity, it sits around forever, and in fact, add to it usually requirements in some sense stable and perhaps time independent in a co-moving frame. But basically there's no really standard definition, but that's the class of sort of things we're looking for. So I'll say a little bit about the history of it before we dive into the particulars of what I want to do. So the history goes back, I guess, to this famous story about Russell chasing a 1/4-degree soliton along the Union Canal in Scotland with it on horseback for miles. Basically, that was the sort of first of the beginning of the iceberg of 1/4 degrees and all the other integral hierarchies. This is not a course on integral hierarchies. Basically, I want to just basically talk about the role of solitons really much more in gravity and in particle physics. Although there are lots of people in this Saclay who really can give a wonderful course, I'm sure, in integral systems and that aspect of it. So in particle physics, they play a very important role in the following sense. In phase transitions. The sort of paradigm simple example of which is in the Ising model, that we'll get more sophisticated in a minute, where basically you have a natural perturbative degree of freedom, the spins on a lattice, freedom. But then you also have this large solitonic wave, the sort of defect wave between, say, lots of plus spins on one side and down spins on the other. And you have a sort of a wave or domain wall. And at low temperatures, that costs a significant amount of energy, whereas at at low temperatures, it costs a significant amount of energy. The spin is a small perturbative degree of freedom, so a very small energy jump when you excite one of those. But as you crank the temperature up, at the critical temperature, this becomes massless, and this becomes the Majorana fermion. So, celebrated example where a solitonic object, this is the soliton, and this is the perturbative degree of freedom, but there are points in the phase space of the theory where the soliton becomes massless, and therefore becomes the more natural degree of freedom with which to describe the theory. So we see this a lot in particle physics, where you have phases of the theory where there are natural perturbative degrees of freedom, and there are where you change the but then you change the coupling constant, you change the temperature, and there are transitions driven by what were very massive solitonic degrees of freedom in one phase, move over to become the low mass or perturbative degrees of freedom in another. And this is a fundamental aspect of string theory, and I just want to make this remark more by way of advertising.
Excuse me.
Sure, please, yes.
I don't understand the language. What is it for a degree of freedom to be perturbative?
You can put arbitrarily low amounts of energy into it.
Okay.
Whereas the soliton usually has an energy cost which is pretty large. And in fact, typically, the sort of thing I'm alluding to, the energy that you've dumped into a soliton here, typically as a soliton, typically goes as 1 over the coupling constant of some power. 1 or 2 in string theory, typically. So therefore, weak coupling, these things become extremely massive. Anyway, all of this is meant as a sort of introduction as to where we're going. But I wanted to just say that for those of you who are going to do string theory and so forth, one of the sort of string theory revolution that was driven 30 years ago almost, or 25 years ago, between M theory and type 2 strings and all these other kinds of strings, is exactly an example of such, where the perturbative degrees of freedom in one domain become the soliton degrees of freedom in another, and vice versa. The solitons of M theory can become the perturbative degrees of freedom in type 2 or in the heterotic string. So, typically, this sort of relationship between the string theories is driven by precisely such an insight. For example, in the heterotic string, you have W bosons, good old-fashioned gauge particles, but in the type 2 theory, they're represented by solitonic branes wrapping cycles. All this to say, there's this very important idea of solitons in string theory and supergravity, which tell us all sorts of relationships between apparently different formulations of the underlying theory, just like in the geodesic model. You have a spin degree of freedom, you have domain walls. Okay, so that's why solitons are sort of broadly interesting. What I want to get to, of course, solitons in gravity. And a priori, this is rather disappointing. So when general relativity theory was first invented in 3+1 dimensions, relativity, it's a beautiful nonlinear theory. Mentions. The question came up, are there solitons? And are there interesting solitons? So the thought was, well, maybe n states of stars or n states of long-term stable lumps could be made out of just knots in the gravitational field. And the answer was basically no. And it's still no. There aren't. And this is largely due to work of Deriving. Are there finite energy, smooth, regular solutions that somehow just sit there forever and are stable over time? Yeah?
So, I know some people were looking into
Geons. These things tend to have time-dependent fields. So I'm saying, well, there are things called cue balls and so forth. There are things like that, but they generally have some kind of time dependence built into them. And if they have a time dependence built into them, they tend to radiate. So yeah, there are things that are seemingly stable, but actually are time dependent in their fields. But basically, if you ask this question just of GR itself, without turning on any background fields, we'll turn on background fields in a minute, just GR, can you make a lump in that field? Part of that game was sort of, part of the background here was there was a story also developed for nonlinearities in Yang-Mills theories or nonlinearities in electromagnetism using Born-Infeld theory, and then you can make interesting lumps. So they thought, okay, in Born-Infeld I can make lumps, can I do it here? And the answer was basically not. Geons, I think they're time dependent, I'm not sure, do you know that? Okay. There are lots of theorems that say no, you can't do this. So basically it went away, but then also with the advent of singularity theorems and parity theorems, the question was changed a little bit. Basically, for the singularity theorems, we learned that singularities are a part of nature. And as a result, people changed the question to the following question. Are there things that look like solitons, but we allow them to have singularities inside horizons? So the question, or the idea of a soliton, was weakened in general relativity theory. So, GR, you now allow singularities inside horizons. And now you ask the question, you're looking for stable, time-independent, solutions with localized energy. Lumps, I'll just call them lumps. And that's where we're going to start. The first of these examples, the answer is yes, and the solutions were generated by Papapetru and Majumdar. I'm going to get to them in a totally different way than they did. But they are very nice localized lumps. Moreover, they are stable, at least in quantum mechanics, as well. In the sense of the Hawking temperature is 0. So they don't even radiate Hawking radiation. So these are about the nearest you can come to this idealized notion of a soliton that lives forever, sticks around forever, and is a lump in the field, and never does anything in time, and therefore because it has Hawking temperature. So that's really what I'm going to start with, because they are not proper solitons. They have singularities, they have horizons. They are intrinsically bad things in that sense, but they are actually the best you can do in 3+1 dimensions for the solitons. Additionally, I want to say a couple of words about BPS-ness and supersymmetry, because that's going to play a very large role in this discussion. So the goal is to look for solitons in whatever theory you've got. And this course is really going to get beyond 3+1 dimensions. We'll go basically to 4+1 and 5+1, where we can find there actually really are solitons without singularities. Why do you want to do this? And so forth, and how do you search for them? So you look, there are two practicalities of looking for solitons. And the second of which is, why do you want to do this? You know, after all, we now know from LIGO and all this kind of stuff that the black holes with horizons are actually a really essential part of nature, or seem to be. So therefore, why would we go looking for something else? I'll do that in a few minutes. That. I want to just say a couple of comments about how you practically go looking for them. And the way you go looking for them is essentially look for BPS objects. And secretly, these are usually supersymmetric. So this is a practicality of life in the sense of these are going to be the most stable of all such things. So what is a BPS object? It's something where you specify the boundary charges, or you specify its charges. Typically electric charges, but there can be other charges you can specify. And then you ask for the lowest energy state you state in that vector. That's what BPS means. You minimize the energy subject to specified charges. That's the Microstate procedure. But secretly, as we'll discuss, these kinds of solutions are always supersymmetric. And they always have, nice thing about them for black holes, they always have T Hawking equal to 0. So as a practicality, if you're looking for solitons, a generic soliton is usually hard to find. You want to find the most stable ground state given some boundary conditions, then you go looking for supersymmetric. It's a Faustian bargain in a way I'm going to describe later. It makes life much easier, so one of the core messages of what I'm going to talk about is how much easier it is to look for these guys, or most particularly the supersymmetric guys, but the Faustian bargain is that you have no Hawking temperature. Okay, and since I'm making introductory comments, I should say why we're going to do this, and this is not a course about the black hole information problem, but my motivation for doing this is absolutely about that problem. Instead, if you came a few minutes late with some lecture notes, which I typed up, they're online, and I think I have a copy or two there somewhere around here. Okay, so why do this? Particularly in the age of EHT and LIGO. The answer really is the black hole information problem, to me at least. It's a mathematically interesting question in its own right. So let me just state what this is and why solitons are making a comeback and talking about this issue. So the black hole information problem, simply put, is that the black hole has an entropy, which is the area measured in, according to the area measured in Planck units. And for the black hole at the center of our galaxy, in the Milky Way, which is about 4 million solar masses, this area is around about, over LP, is around about 10 to the 90. That means the number of microstates that must be inside that black hole is a ridiculously large number, e to the 10 to the 90. Seen from outside, black hole uniqueness tells you that there is, given the charge and angular momentum and mass of the black hole, there is exactly one state. And so the problem becomes the following. Inside the black hole, there's an insane number of microstates. Outside the black hole, you only see one state given the charge, mass, and angular momentum, and these two numbers aren't equal. It's not such a problem until you factor in Hawking radiation. And then what happens is if this evaporates, all these e to the 10 to the 90 states have to come out of the black hole, or if it remains Hawking radiation and it remains completely thermal, then basically you have this problem that the thing that evaporates into only has one state, because Hawking radiation is made by pair creation outside the horizon. And so therefore Hawking radiation can never encode anything inside the horizon, and therefore it will only ever see this one state. So Hawking radiation is also unique, up to some very bossy factors, will reflect this state and not the other side. And so the problem becomes all the more chronic when you have Hawking radiation, because those states ought to come back. Alternatively, you have some horrible problem where the initial states can never be reconstructed from the final state. There's no unitary evolution from e to the 10 to the 90 states into one state of the system. Put differently, you can make the black hole in many, many different ways. You make it out of hydrogen, helium, politicians, gilets jaunes, make it out of whoever you like, but the output is always universal, and it's always one state, and therefore you cannot reconstruct it, therefore this violates unitarity in quantum mechanics. Okay, so now, there's an old story about how you beat this. The old story about how you beat this is, you look at the evaporation timescale. The evaporation timescale is huge. So the torque for evaporation is roughly 10 to the 67 years times the mass of the black hole divided by the mass of the sun cubed. So for the guy in the middle of the galaxy, we're talking about 10 to the 87 years. So the idea is, well, you know, you get a lot of information, but you've got 10 to the 87 years to get it out. So maybe a tiny correction, tiny correction, maybe a quantum correction to GR over 10 to the 87 years, 10 to 67 years, to lead to information retrieval. And this was basically a fairly reasonable attitude. In fact, I had a conversation with Ed Whitney in Rome about a decade ago at Strings, and he advanced this argument and said, why do you do this? Because tiny corrections will fix the problem. The answer is wrong. And in fact, this was basically nailed by Mathure's small corrections theorem in 2009.
Sorry,
Let me write down unaltered corrections theorem. Yeah.
May I maybe suggest that you're making a bit too strong a statement?
Yeah, you certainly can.
Because I guess you have to say what Mathure's assumptions.
I know, I'm going to say something about it.
And it's very likely those assumptions are not satisfied.
Indeed. So hold a second. Before we start this debate, I've said this to create an argument. So, one second. So let me just simply say, what he says is essentially there have to be order one changes to the physics of the horizon. In other words, he makes a bunch of, wait a second. I'm saying what Mathure says. Nothing can be, I'm quoting him, we can argue about whether he's right. The physics at horizon scale. That's what he argues. And he makes three basic assumptions which reasonable people can differ on the validity of, but they are actually pretty reasonable assumptions, and therefore you have to make some change to those assumptions in order to avoid this problem. So go for it, Monica.
Yeah, so I guess when you say that this has been shown wrong by Mathure,
This idea is based...
It's based on assumptions, and one of the assumptions that he makes is incredibly strong, which is the assumption that the physics behind the horizon is independent of the physics outside the horizon.
Yeah, I know, okay.
And that assumption is likely failing.
Okay.
And probably if you discuss with Wickham now,
You
it
cannot
would be...
No, okay. So let me explain the context of this. I've had many conversations about this over the years, and most people make exactly the assumptions Mathure makes. And so if you look at the assumptions Mathure's making, which are reasonable, okay. So reasonable people can differ on this, but there's a general consensus that you're going to have to change something about the horizon scale physics.
There is no general consensus that you have to change something about horizon.
You can change the Copenhagen interpretation of quantum mechanics, and then indeed you don't have to change. But if you keep the Copenhagen interpretation, you have to change.
Okay.
If you give up Copenhagen,
I don't think I'll picture anymore. But okay. So
I
here's
just want to make a correct statement. I think I don't think it's true that the consensus in the literature is that near horizon physics has to change. There are other ways around Mathure's theorem, one of which that I think a lot of people adhere to, is that simply you have physics behind the horizon depends on what's going on around outside.
Yeah, so information can propagate across the horizon. Okay, wait.
Okay,
guys,
give us Copenhagen break.
this is a graduate course. What you should take away from this, is that serious people disagree entirely on it. It's a great place to do research, right? Sorry.
A different question, sorry. Even if you don't have to wait 10 to the 67 years, it seems, because even instantaneously, the evaporation has to leak a large number of states, of microstates.
Actually, the problem is also because every black hole is never found in a 0 Kelvin environment. So in fact, even these black holes are still swallowing. The temperature of this thing is 10 to the minus, 10 to the minus 10 Kelvin. So basically, it's already in a 3K environment. It's never going to Hawking radiate until the universe has expanded hugely. But the Hawking the micro background is down below 10 to the minus 10 Kelvin. So we won't ever see this today unless we make one of the particle accelerator. Okay, so reasonable people can differ on what we need to do at the horizon. But the whole point about revisiting solitons is to answer the following question. If you want, can you find a way to support you find smooth, horizonless, and this is really what the course is about, geometries that look like black holes to arbitrary precision outside the horizon. And these things are called microstate geometries. And what you should think of them as also is not just a replacement for black holes, but as a classical support mechanism for horizon scale microstructure. That's why they're interesting, and even if you don't buy into the whole story of Mathura and so forth, they are still interesting solutions, and if you want to support structure at the horizon scale, this is what you're trying to do, and this is why I do this. I want to find things of replacing black hole horizons by something that looks just like a black hole, with arbitrary precision, that actually gives you a physical support mechanism. And so in some sense it makes a black hole no more mysterious than a neutron star, well, except... Sure, please.
Question. The kind of counting of Schrödinger and Buffer,
Yes?
it's still about standard black hole solutions, no?
It's about a very special black hole solution.
but
It's
still
BPS.
Black hole.
Yeah.
In this case, in principle, you shouldn't have problems with the military, you know? Because
You won't, and that's the idea of the, they're counting states, but they're doing BPS, they're doing it at zero coupling, not just weak coupling, zero coupling effectively. So,
And then it's saying actually that, when you have the Schrödinger Buffer black hole, because the temperature is zero, there will be no evaporation, so then there's no paradox.
well, there is
No,
also,
it's
there's
not-
also a storage problem. Remember that if you've got a horizon, even at zero Hawking temperature, it's got a big horizon, which means it's still got a big entropy, and that reflects the information that's stored inside the thing. So then what you can do is you look at these BPS solutions as sort of very stable islands of stability inside the configuration space you want to look at. You look at the storage of information, and then you maybe heat it up a bit by dropping stuff in. So that's the kind of evolution we're trying to make. But I don't think I've answered your question.
no, I'm not sure why if you have a kind of regular black hole, you always have information paradox. In this sense, because in this kind of
Okay, so Schrödinger-Buffer is zero coupling, so 0 G Newton, and it's BPS. So it's really a funny corner of this phase space. So another way you can phrase what I'm trying to do here is I'm trying to take Schrödinger-Buffer and turn on G Newton. That's really what I'm trying to do. And then what we try and do is then do the fully holographic description of those states. So what we've in fact done in the last few years is precisely taking Schrödinger-Buffer and turning on G Newton to see what the holography tells us about those states. Okay, so that's enough of the blah blah. I'm going to start getting down to specifics. And I want to start very simply at the other end of the story. So, very Nordstrom solution. So, since there are many graduate students, I will now start at basically a beginning graduate level. I'm going to assume you know some GR, and I'm going to revisit this whole solution that's been known since about 1920. I think Ryzen did it in 1916 or part of it. So it's about from 1916 to about 1920. In the first 4 or 5 years after general relativity was invented. And if you haven't seen this, fine. If you have seen it, I'm going to go fairly rapidly through it. Details are in my notes. But my purpose in doing this is I want to go through the basics of this class of solutions to highlight many of the features that we're going to see later in supersymmetric solutions. So this is the cheapest way of getting a supersymmetric solution and understanding the sort of universal elements of it. So, any questions over before I do? I'm spent much more on the blah blah than I intended to, but okay. Questions or comments? Monica, go for it.
No, just concerning the motivation, because sometimes you mention LIGO and so on.
Yep.
So, I mean, it could happen that the black hole-like objects that they see were some sort of large solitons,
Yep.
and they might have some multiple moments and so on. Do you have any idea about the experimental precision on measuring those multiple moments?
I have no idea, but I think
This I will measure,
I
this
think
I will measure like 7 or 8 dipole moments. So to be able to distinguish between essentially I mean there are people who do extreme massless spirals. I'm part of the design collaboration. So they actually measure both dipole, quadrupole, octopole, and they'll measure 5 or 6 things. So if you have a boson star, for example, which is the simplest toy model, which is not working in theory, then we have an extra parameter, and you can rule it out. when you have, you can hook up something with like 2 or 3 extra parameters, but that's very complicated. Here, these things will have some, infinite series of things. So, there'll be some numbers predicted of this if one ever does real black holes.
Okay, so let me make a quick comment. The best way of thinking about anything that comes out of LIGO is you think about the light crossing time of the object that's collapsing. So if you've got a 30 solar mass black hole that's 90 kilometers in radius, 180 kilometers in radius, light crossing time is measured in milliseconds or tenths of milliseconds, which means that the time scales are, so the wavelengths we're looking at are kilohertz and above. LIGO can only see 400 hertz and above, and below. So LIGO is not like to see the level of detail that you need to do any of this, unless you see an awful lot of events. So the takeaway message is LIGO is 400 hertz and less, and therefore that means a millisecond, which means something's going to be 300 kilometers in size as a light crossing time. So unless you've got something that's 100 solar masses, you're not going to get down to LIGO. LIGO multipole moments. The monopole moment you can see.
And another question, which is also related, because most of the solutions that you can construct are modeling extremal black holes.
Sorry?
Most of the solutions
Yes.
that we're going to talk about, they model extremal black holes, whereas real black holes usually are not.
Absolutely.
Close to externality. So can you say anything about, comparing to?
Well, okay. So I'm trying to start to get the course back down to earth, and I'm trying to get back down to something really simple so that the graduate students can follow along. But the short answer is we can make very isolated, extremely special examples of black holes that are extreme or aren't BPS, or we can make, in principle, small temperature heating up, small motions on moduli spaces. So we're far from getting something that is generic when it comes to non-BPS. But for the BPS story, we've got a lot of control now.
Yeah,
I mean, you know the answer to this question, Monica. So is there
my
any?
question was just motivational, just to understand, even if you have very few solutions, can you compare anything in principle to today?
Okay. The answer to that question is I can get general stories and general threads out. Like, for example, the universe doesn't have super QCD. It's QCD, but we learn a lot about QCD by doing super QCD. We can learn things about microstate structure by looking at the supersymmetric counterparts and trying to pull out universal threads. So in the same way that we study QCD, it's useful to study super QCD. It is useful to study microstates and their supersymmetric counterparts because you can calculate them and then hopefully pull out some universal stories. So that's the best answer to that question. Okay, so let me get down to it. I want to start illustrating now. So for the rest of you who are advanced in this is going to now be very, very basic. We're going to start talking about the most general spherically symmetric metric in 3+1 dimensions. Metric in 3+1 dimensions. And now I'm starting where a graduate course would start. And the first thing you do is you say, okay, well, it's going to have a radial coordinate and time independent. Let's make it easy. So, spherically symmetric, time independent. Everything's going to be a function of radial coordinate. There will be a minus dt squared. There could be, in principle, e to the 2 beta. This could be a function of r dr squared. There could, in fact, be a cross term, e to the 2 gamma r dr dt. And then there could be some other function, e to the delta of r, 2 delta of r. And now to make it spherically symmetric, we use the metric on the sphere. So there's the spherical symmetry built in. We assume that basically the whole space is sectioned by spheres. Okay, now, first things first. The usual setup here is that you're now going to fix all your sort of gauge degrees of freedom. And in particular, you have the freedom to redefine R. So you can replace R by R of some other R twiddle. And it's still an equally good spherically symmetric metric. So to fix that, the canonical way to fix it, that parameterization, is choose e to the 2 delta of r to be r squared. That fixes your ability to reparameterize the radial coordinate in any way you like. So now we fix what radii are, or equivalently, the radial coordinate is defined in black holes to make every sphere have an area of 4 pi r squared. That's the definition of the radial coordinate. The other thing you can also do is you can place t by this plus some other function f of r. And then dt picks up a piece which is dt twiddle plus f prime of r dr. And then dt squared picks up a piece which is dt twiddle squared plus 2f prime r dr dt plus df prime squared dr squared. The whole point of this f prime is that we can choose it so that in this metric here we kill off that term. So in fact, the general spherically symmetric metric is ds squared is equal to e to the 2 alpha r dt squared minus e to the 2 beta of r dr squared plus r squared dt squared sine squared theta d phi squared. So, starting point, we're going to look for spherically symmetric time-independent solutions, and that's the metric we start with. Now, we're in basic graduate student land. So, graduate students, any questions? Anybody puzzled? Part of the game here is for me to understand what you know and how I need to adjust subsequent lectures. So please jump in, or you're confused about something, jump in. Okay, so now we're going to couple this to the electromagnetic field. So having picked the metric, we now turn on generally spherically symmetric electromagnetic field. And there are two terms you can add. But the Maxwell field, I'm going to assume you know two forms or forms. There's an electric field, which is basically dr wedge dt, or the t wedge dr, I think is the one, right? T wedge dr, and then plus, what you'll call p, sine squared, sine theta, d theta, wedge d phi. That's the most general spherically symmetric electromagnetic field. In particular, this is obviously spherically symmetric because the sphere is here, and this is the volume form on S2. And in particular, E is a function of R alone, but P is a constant because you have to have D of F is equal to 0. And if P depended on R, that would not be 0. I'm going to keep things simpler. In the notes I've put allowed P to continue. I'm going to put P equals 0. It's the magnetic charge. I'm going to get rid of it. I'm really interested in this guy. And of course, F is equal to dA. And A is now equal to phi r dt. And you have phi prime of r is the electric field up to a sine. So that's the most general spherically symmetric electromagnetic field, and I'm going to kill off the magnetic monopole moments, although you can continue happily with them. Right, so what are we supposed to do? And I'll only do this once, I'll do it very briefly. You solve Einstein's equations. So you take this metric, you compute its Ricci tensor, and you write down Einstein's equations in their other form, h pi g, t mu mu minus, I think that's a half, t g mu mu. T is, of course, the trace of the angular momentum tensor, and t mu mu is equal to, I even got the factors of 4 pi straight at the moment, or at least I believe I did, f mu rho minus 1/4 f g mu f squared. So, if you're going at this straight at this, you simply want to set up this set of equations, and with this with energy momentum tensor, with this field, and so forth. Any questions at this point? I want to know whether you're with me, whether you've understood everything. Anthony, is it good?
Yes.
Good. Okay. He's my token graduate student, I kind of know. Good. Okay, so rather than go through the horrible tedium of doing this, I actually prepared exactly one slide, which I'm now going to try and get up on the screen. I think that's the mute button. It's off.
It's the bottom of the corner.
And if I want to have a shot, I'll just wait for it to bring up here too. Oh, it's on the scene.
No, it's going.
It's
coming.
It's coming. Okay, good. Okay, so basically, the reason why I'm going to this level of detail is I want you to appreciate how horrible this process is, and I'll explain how horrible it is. In a second, we got some light here.
You have to put the file on the.
Okay, so in preparation for this is in the notes, by the way. So here's the metric I'm advertising, and here's its Ritchie tensor. And so what you're supposed to do now is calculate the energy tensor for this. I put the magnetic fields in as well. Here's the components of the electromagnetic field. There's, I think, a sign error in the notes I noticed, which I fixed. Should be a plus sign. And so it looks terrible. The reason I want to show you how awful it is because if you imagine having two variables, it would become a complete nightmare if it was a function of, r and theta or something like this. But it turns out it's not so bad to solve this system. So basically, you said about solving it the following way. You look for the easiest equations first. And the easiest equations come from the fact that this and this are almost the same up to a factor. So you look for the Einstein equations. Let me call this, let me subtract that and call that 0. I'll call that Einstein mu. And if you look at the equation of Einstein 0, 0, and let me get it right, it's e to the Einstein 1, 1 plus e to the 2 beta minus 2 alpha Einstein 0, 0. The whole point is these terms exactly cancel, and almost these two terms exactly cancel, and you get something really simple, which you're very lucky. It's basically alpha prime plus beta prime is equal to 0. The only terms that survive are these two terms here and here. Okay, so that gives you a nice piece of bootstrapping. It tells you that alpha is equal to minus beta plus a constant. But you can get rid of the constant by rescaling t. T goes to a constant times t, lambda times t. You can get rid of this constant. And so alpha is equal to minus beta. Okay, so now you go work a bit harder, and it turns out this guy is the next best guy. And so with alpha is minus beta, you can rewrite this thing here as basically something like r of r e to the 2 alpha r. And then the right-hand side, let me cheat and use my notes. Oops, lost it. Where's it gone? The right-hand side becomes, where's it gone? Oh, the alpha is equal to 1 plus p squared over r squared. Oh, q squared over r squared. So basically, this, the 2 term becomes rather simple. Essentially, when you start looking at this term alpha is minus beta, so that goes away, and you get the electric field squared multiplied by r squared. That gives you.
What is q? Sorry.
Q is, I'm sorry, I got ahead of myself. Is equal to 1 plus the electric field squared times r squared. Okay, now, the other thing you also get is, of course, Maxwell's equations. Remember, you have that f is equal to minus, or even it's not minus, it's e of r, the r dt. I expect you, particularly before next time, to know about duality of forms. Maxwell's equation of d star f is equal to 0. And that tells you that in this case you get d of r, e of r squared, d of r squared is equal to 0. There is, in fact, up in here, if you do it right, an e to the 2 alpha plus beta coming from the metric, but since alpha is minus beta, it goes away. So therefore, E of R is Q squared over is Q over R squared. And so Q is the electric charge. It's the solution to the Maxwell equation. So basically, you have to impose Maxwell's equations. It tells you that essentially the divergence of the electric field with volume factors is 0, and it gives you this sort of familiar result that the electric field is Q over R squared, or the scalar potential is minus Q over R. So you put it in here, and that becomes 1 plus Q squared over R squared, because you get R to the fourth. Okay? Right. And so, at the end of the day, you get alpha primed. So you get from this equation, you then get alpha primed. You can integrate, you get alpha, e to the 2 alpha, excuse me. Well, you simply integrate this thing. And did I get a Simon? I probably did. Let me check my notes again. Is equal to, I've got it wrong, it's 1 minus. 1 minus, and there's a minus here. So basically there's the 1 R Q squared over R plus a constant of integration, mu. And so therefore e to the 2 alpha, which is equal to e to the minus 2 beta, is equal to 1. Let's see, did I do this wrong? I get R when I integrate, sorry. Integrate 1 gives you R, integrate Q squared over R squared gives me minus Q over R, constant of integration. Now I get 1 plus, and I write it as this way, 2m over R plus Q squared over R squared. Okay, so at the end of the day, you solve this differential equation, and then you check that it satisfies the last one. So what I did was I used a combination of these two guys, and I used this guy, but I didn't use those two independently. The last equation is always guaranteed to work. A very simple reason. The Bianchi identities, you know that this thing has a vanishing divergence, or the energy momentum test has a vanishing divergence. So one equation guaranteed to work for free. So therefore, you're done, but you can check it and it satisfies the equations of motion. So basically, it becomes rather easy once you unpack it. The thing looks terrifying at first, solving this system of equations. But by taking clever little linear combinations, you first of all figure out that alpha is minus beta, and then you look at pick off the easy equations first, and then check it solves the rest of them. And believe me, it does. This is the Horizonless solution. So, Horizonless. Now I'm going to just spend some time talking about what this is and why it's supersymmetric, or can be made supersymmetric. ds squared is equal to minus...
Sorry.
I'll explain what m is in a minute. Hang on a sec, let me write it down and I'll pause.
Okay.
T squared, I always get the powers the wrong way around. This one's a minus 1, yes. I'll explain why I've identified this as m in a minute. Squared plus, that's the minus 1, and then that's r squared, t theta squared, plus sine squared theta, d phi squared. Sorry, question, yeah?
No, you answered my question. There is a minus compared to the previous slide. So
There's a constant of integration, I should call it 2 mu or mu over r.
Okay.
How do you identify it? Because remember that in the Newtonian approximation, g naught naught is always minus 1 in Gaussian space, and then what turns up here is 2 times the Newtonian potential as a function of x divided by c squared, or something like that. And so what you do is you figure out this constant integration is the mass by comparing to the Newtonian limit. And of course this is m over r or gm over r. Okay. Happy so far? So we have this thing, and this is really where I want to start. dissecting, this is the general charged spherically symmetric time-independent black hole. Planet, for that matter. Vacuum blue, symmetric, charged planet, star, or black hole. And it's valid outside the matter that makes the solution. And this is the solution that was obtained by around about 1920. Very quickly after the solution, you can get rid of this, I think now. Use this. That's all I'm going to use that for. And the equations I solved are in the notes. Can we get the lights back up here? Okay. Now, I want to take one more limit of it, but let me pause. Any questions or concerns, issues?
Just a curiosity, this Nordstrom is the same which he had this scalar theory before Einstein? Or
I think it's the same one. Gunnar Nordstrom, I think, yeah. I think exactly the same. This is the guy who had the conformal gravity theory and said the metric should be e to the 5 times e to the mu.
it was just a scalar theory of gravity?
Yeah, I think it was. Nordstrom theory is where you assume that it reduces to the following, where you make the e to mu. So you can track whatever. And so perfectly consistent with this. Trouble is, it's a conformal theory and doesn't deflect light because the light cones are unperturbed by conformal
This
transformation.
was before Einstein, I think.
It was before Einstein, but the deflection of light by the sun is what killed off Nordstrom theory. Okay. So now I want to take the limit, which is the Faustian bargain of supersymmetry. We're going to largely consider extremal cases. Is m equals q. Now, I'll explain what that means in practice. So if you want to look for the horizons of this guy before we put the m equals q, you look for the horizons. Now, this is actually a simple algorithm for time-independent solutions in general relativity theory. It's very easy to find the horizons. You look at the inverse metric, the upper R component, and set it to 0. Not immediately obvious why it's that choice, but I'm happy to explain, if you haven't seen this before, that basically
Why
this
not
is,
G0 0 equal to 0?
because that's everything to do with time. So what are you looking for with the horizons? You're looking for a null hypersurface, closed or compact. Sometimes setting G00 to 0 works, but this is the right way to do it because what you're looking for is a closed surface, the horizon, such that all the light cones on the surface tilt into the surface, everywhere on the surface. So basically you're looking for a surface where the light cones are tangent to it. So if I look at this surface and say it's defined by some function of x, the coordinates being 0, okay? It's going to be a null surface. That means that the normal vector nu must be null everywhere. That means that since the normal is proportional to the gradient of the function that defines the surface, then basically the statement that it is null everywhere on the surface is equal to 0. And that's the same as saying gradient of mu of f g mu. Now, the whole point about this surface is, well, x equals a constant, is that these constant surfaces, as they go out, define compact surfaces, and you're interested precisely at the point where this compact surface, fx equals constant, is making a null surface, where the normals are all null vectors. But if you think about this for a second, you define this to be a new coordinate, r twiddle. And the smart thing to do is to arrange your radial coordinate so that outside this horizon it's a nice space-like surface, and as you go in, or time-like surface, and as you go in, it suddenly becomes null. And look at what this equation is. That is the equation G r twiddle, written in terms of this new coordinate that's sectioning the space, is 0. So this is how you, if you've not seen this before in GR, if you have, well, good, but the basic idea is, if you're looking for a time-independent solution, you section the space by surfaces such that they're nice, regular, spherical, whatever surfaces out here, they're nice time-like surfaces, and then you suddenly go null at some point. You detect that with the function f of x, and you redefine your radial coordinate such that you're using that as your radial coordinate. And if you look at this metric, it has exactly that property. You look at the point where 1 minus 2m over r plus q squared over r squared is equal to 0. As Joseph points out, it's the same as g naught naught being 0, but technically the most universal way of doing this in a time-dependent metric is you look at the inverse metric in the radial direction and look for the zeros of that. It's the same thing. Okay? So, we are here. Any questions? Does that answer your question, Joseph?
Yeah.
Okay, good. So,
Yeah, is this condition invariant by the choice of gauge you made at the beginning for time and?
no, it's not. I'm cheating slightly.
Okay.
But the point is that the choice of gauge I made at the beginning was precisely so that I could solve the equations easily. So now, in general, what you might ask is, what's the condition on this function f? You want to have r as a constant surfaces. So you look at the r as constant surfaces, you cross off with the r squared, and you see it's spheres times time. So it's a nice time-like surface. But when you hit the vanishing of this thing, the time coordinate goes crazy. But the point is, you've actually you found that point because this surface is now about to become a null surface. Okay, does the time coordinate go to 0? You see that goes to 0, and the surface degenerates and becomes a null surface. So this is the universal way of doing this, but you're fortunate in the gauge choice I chose before, it gave you precisely such sets of surfaces that are constant surfaces with things that section the space into time-like surfaces, which when this vanishes become null. And that's the definition, at least in the static solution, of a horizon. Okay, so look at the zeros of this, and there are two of them. So the solutions of this are, let me say that this is r squared into 1 minus 2m over r plus q squared over r squared is equal to r minus r plus r minus r minus, which where r plus and minus are simply m plus or minus the square root of q squared minus q squared. So, first criterion is that you're going to have n greater than or equal to q to avoid naked singularities. And there's a whole cosmic censorship principle that argues that you can't make a star with n bigger than q, so therefore you won't worry about it. But you better have n bigger than or equal to q. And the extremal case, when the two horizons come together, r plus is equal to r minus is exactly the same as m equals q, and it's equal to q. And this is the extremal case. And in particular, this quantity 1 minus 2m over r squared, this is important for a minute, over q squared over r squared is equal to 1 over r squared r minus q squared, which becomes a perfect square. So basically, in the Weissenholz solution, the mass has to be bigger than q, or bigger than or equal to q, to avoid naked singularities. There are also arguments that you can never make a black hole, you can never charge up a black hole where the m is less than q, or q exceeds m. And so this is, in fact, turns out, the BPS bound for these objects. It says that if you're given a certain amount of charge, there has to be a mass that's greater or equal to that amount of charge, and it's saturated by the extremal object, and this is the BPS object. So, BPS objects are extremely special. They are things that saturate the bounds between energy and charge. They have extremely special geometry, which we're now going to spend a chunk of time looking at. Let's see, we've now spent 5 minutes just about a couple more steps, and then we'll pause and for a break. But they're very, very special objects, and they are the easiest objects to find in this whole game. And also in the notes, I'm not going to do it here, in the notes I've written down or calculated for you by a cheap trick the Hawking temperature of a general rising Nordstrom black hole, and I've explained how to do it. I'm not going to do it here, but it has a Hawking temperature, or T Hawking, is proportional to n minus q and some other factors, but the important point is it goes to 0 for BPS. I'm not going to go into it because there isn't enough time here. So we have the extremal solution, and I want to write it in its canonical form. So now we're going to spend our time basically doing these extremal guys, or BPS guys, and they have the form minus h squared, or h of r squared, plus times dt squared, plus h of r squared, r squared, plus r squared, sine squared, r squared, theta squared, plus sine squared theta, phi squared. And I'm going to massage this a tad more, but let me just make sure I've got the h. One is a positive power and one is a negative power. The first one is the minus 2. And h of r is equal to 1 minus q over r squared after the minus 1. So, the extremal guys have a very special form. Obviously, this and this are inverses of each other. That's part of the Rising-Nordstrom story. But now it's perfect square of this quantity. I'm going to take one last massage of this thing to get where I want to be. I'm going to change coordinates a little bit. I'm going to introduce a new coordinate, rho, which is rather trivial, but rho is r minus q. And so you see that h is equal to 1 plus q over rho. And in fact, if you do the whole change of variables carefully, you'll see that this is nothing other than minus h squared, h minus 2, dt squared. And now I'm going to pull out h squared of this, and you get d rho squared, plus rho squared, sine squared theta, or squared, theta squared, plus sine squared theta, phi squared. And we put our So another way of illustrating how special these extremal black holes are is essentially there is one function, h, here and here. This this metric here is flat space. Moreover, h is harmonic. On a three-dimensional space is 0 on R3. This is R3. Moreover, the Maxwell field, let me write as gauge to F is equal to dA. And you can check that the Maxwell field's gauge potential A is h to the minus 1 times dt. So in particular, what happens to these extremal guys is extremely simple. There is one function, h, which turns up in the metric, warping it in this particular way. It also turns same functions exactly the electrostatic potential. I've cheated slightly. That is now 1 plus q over r dt. I've cheated. I've added a constant, which I can do. But basically, sorry?
1 plus q over r to the minus 1.
R to the minus q over r. Sorry, thank you. Thank you very much. Yeah, and probably with a minus sign.
No, plus.
No. Plus, minus. It really is q over r. Because this is
The harmonic function is
this is r minus q over r to the minus 1, commonly written as therefore rho minus q over rho. Up to the sides, I think, or rho plus q or something like that.
plus q over rho, yes.
There we
Rho
go.
plus q over rho.
Okay, so that's h.
But h is a plus.
Okay, there's a plus or minus sign.
No. The power is minus, and
Oh yes, indeed.
and in
This is the minus 1,
yes, and inside
which is
plus.
but this function is basically 1 plus q
over
over
r.
rho.
Sorry, it's your r, not your rho.
Minus 1.
Yes. Sorry.
Okay, so you've done something very, okay, what I want to finish on is, you've done something very weird to get this form. You have written this new coordinate where you've shifted the radial coordinate by minus q. So this is a very weird, this is meant as a warning for everything we're going to do. This is the full extremal metric. And you can do Eddington, Finkelstein coordinates, go across the horizon and everything else. To get to this form, we've shifted the coordinates. And the horizon was at r equals q, which is equivalent to rho is equal to 0. And the singularity is r is equal to 0, which corresponds to rho is minus q, which is when the function h goes to 0 or something, or h goes to infinity. Let's see, r, h is...
It goes to me.
Goes to infinity, yeah. So we are going to be working with this thing which is h of rho, which is this 1 plus q over rho. And you will generally encounter this form, but you should remember that rho is 0 is not the singularity of this solution, or any of these solutions. It is actually going to be where the horizon would be. But notice what we've got by going into this route. We have something which is the form ds squared for is some harmonic, some object h to minus 2 t squared plus h squared, and then we write it dy dot dy. So this is flat R3. And that the electrostatic potential, A, is equal to minus, basically H plus H to minus 1 dt. And H is harmonic on, H is harmonic on R3. This is not an accident. This is actually completely generic for this class of solutions. But basically, at the end of the day, we have a flat space section, we have a harmonic function, and that harmonic function turns up in the metric with certain powers, and it also turns up as an electrostatic potential. So I was asked to make a break. Now is a very natural time to make a sort of 10-minute coffee break, and then I'll pick up with this. And I'll talk exactly about why this is supersymmetric, but I'll also talk about various, I'll start by talking about the various limits of this metric. But for the moment, let's take a 10-minute break and coffee and whatever.
Thanks.
Sorry,
Yeah.
where does the classical Schwarzschild black hole fit in?
Q equals 0. Q equals 0.
Okay.
But you can't have, it's Q equals 0, but you can't have M as Q.